Okay, our next speaker is Vincent Herrmann, and we talk about interestingness as an inductive heuristic for physical comparison progress.
Okay, yeah, thank you very much. I hope people can understand me also online. I mean, my microphone is still turned off, but is there a room microphone that picks up? Okay, so it should work. Okay, great. I'm very happy to be here. Thank you to the organizers. It's already been very interesting, and I think it will be also super interesting in the future. This or in the coming days, this symposium. So yes, I'm talking about interestingness, specifically interestingness as an inductive heuristic for future compression progress. Maybe like one sentence about me. I'm Vincent. I'm just finishing my PhD in Lugano, Switzerland, the ITSIA Institute. So yes, I think in recent years, or at least since the deep learning boom and even more the last few years, we've become very good at basic learning from data and achieving specified tasks. We have large neural networks, we have gradient descent, we have reinforcement learning techniques. So if we have some data, some environment, some problems, we have some pretty good tools how to solve that. I mean, in LLMs, this now all comes together. We have the pre-training phase with gradient descent, then we have post-training, fine-tuning, using RL, using verifiable rewards, using human feedback, all that sort of stuff. But yeah, then we can already see that basically the left side here, the training data, the tasks and problems, they're human-defined. Like there are thousands of researchers, thousands of experts, data labelers that are creating, I mean, they have created the data, they're creating training environments, they're doing all sorts of stuff to help the model grow. The model doesn't go get better, or each new generation of a language model, for example, doesn't get better by itself. Like there's a lot of work going into that. But if you want to truly create like open-ended intelligence systems that self-improve, kind of want to close the loop, somehow have the model create its own training data, its own problems, define its own tasks. Yeah, but that it's not that easy. If we do that naively, for example, if you train a generative model on the data that it already generates, the previous iteration, you get model collapse, like the model just ceases to do anything interesting or to create any novelty, basically the distribution collapses. So what I'm proposing, or what I think is pretty clear, is that we need something. Like humans, we have a taste for what to do next, what to feed the model in order to get some new stuff. And maybe we should think about how to define that, how to quantify that. We need something like an interestingness criterion. And yeah, what I'm presenting here now in this talk is based mostly on this very recent SML paper, yeah, which I did with my PhD advisor, Jürgen Schmidhuber. So thinking about interestingness and criteria for interestingness is not a new thing. Like people have thought about that. Also in the field of exploration, intrinsic motivation, and so on. One very simple idea might be that an object is interesting if it's uncommon, if we haven't encountered it as much as other objects. Maybe that works, but of course it only works if we can actually count the objects and basically have a finite repertoire of objects. Then we can say, okay, the one that we haven't seen as much is the most interesting one, or the most rare one. If we have infinitely many, or we have a big world, then we need maybe something like a model that assigns some probability to an object. And then we can maybe say an object that our model assigns very little probability to is interesting, is surprising in the Shannon sense. And that might be interesting. So if we chase that, we're kind of adversarial. We're trying to look at objects that the model cannot really predict. So we use prediction error as an interesting criteria. That also works in certain settings, but these things have a certain problem, namely that they don't differentiate between what we might call aleatoric or irreducible uncertainty and epistemic and reducible uncertainty. And if we don't do that, we might get stuck in these kind of aleatoric environments that are just inherently random. So the classic example is that the agent might get stuck in front of a noisy TV because there's always new noise that it cannot predict, but there's also, I mean, I think we could say nothing interesting going on in the noisy, very random environment. So one solution to that is not look at the uncertainty or whatever, but yeah, to look at the change that an object induces in some kind of subject in the system. And there are now three, I would say, very related ideas. One of them is information gain. This is a very classically information theoretic formulation and very probabilistic. It's basically if we have some prior distribution over beliefs, let's say, and we are presented with an object, then we're measuring how much does this object change this distribution over beliefs. Another criterion might be learning progress. So if you're trying to achieve some skill, we have some learning criterion. Then if an object helps us improving this criterion, this is what we would call learning progress. And this is, of course, a very like optimization based idea. Like we are looking at how much an object helps us optimizing some function. Now the last one that is also very related, and this is the one that actually we talk about most, is compression progress. This is rooted in algorithmic information theory, I would say. That means that does a new object help us reduce the description length of a whole history, experiences, and so on. This is also something that my advisor, of course, has written and talked a lot about. I think we can maybe see that these three criteria seem to be very related. They're all about if an object helps change some worldview, some function, some description lengths, or if it induces some understanding. I think if I've seen the program of the symposium correctly, we will also hear more about the exact connection between compression and learning, and so on. So, very interesting. What I want to say quickly is that these three criteria, I mean, they're definitely very related, but maybe they're not identical. Namely, for example, you can show that not all learning progress is information gain, because we can, for example, optimize non-probabilistic criteria, and then it's not really the same thing. Also, information gain is not necessarily the same as compression progress, because information gain also counts compression setback. Like if the description length gets worse, that's also some kind of information gain. So it's not exactly the same thing. And learning progress and compression progress are also not always the same, because compression progress has to take the complexity of the model into account, which learning progress usually doesn't. Okay, one other, I would say, maybe disadvantage, or why these things are not as practical, is that they only can calculate it post hoc. If the system has integrated the object, then we know how much compression progress, learning progress, information gain we've made. But if you think about closing the loop, that doesn't really work. We want to have a criterion that tells us before we put in the work how promising some kind of object, some data is. Of course, we can try to predict compression progress, learning progress, information gain. And this is also what's being done sometimes. Can train a model to do that, for example. But it's tricky, right? Because, it's very non-stationary. Objects that have been interesting become boring. Like something we have, once we gain the insight, it ceases to be interesting. So it has to, like, the predictive model also always has to update itself. It might also be costly to compute the criterion. For example, if we talk about large neural systems, we need to do a whole training iteration to even get one value of compression progress, let's say. And then there's a problem of data assignment. If we do for example, a gradient descent based optimization, we don't know, like, this particular object, has this now improved the compression of the learning, or was it any of the other examples? So it's tricky. So how predictable is compressibility? And what I want to show is that using algorithmic information theory can kind of sidestep, at least in theory, all these issues that that's okay. So and that is also exactly what our definition of interesting is about. We say that interestingness is an heuristic, like it's the expected future compression progress under further engagement. So I think this captures quite well also intuitively what we mean if we say something is interesting. I think I call something interesting if I expect that if I engage with it, I will learn something. I will gain insights. There's something I can learn from an object. sometimes, like if I recommend a book to a friend and say this book is interesting, okay, I mean maybe I have already learned something from it, but my friend, then I mean that I expect my friend to gain some insights about something from this book. So I think interestingness is inherently about the future, about future learning, about future insights, about future compression. To normalize it a little bit more, maybe you can think about it like that. You can think of an agent which has already a history of experiences. They might be already a bit compressed or not, that does not really matter. And now it encounters a new object. And now it spends some time and computational effort to compress the joint description length of these two things, of the history of the experiences and the new object. And however many bits it has saved using this computation that it did, that is what we call compression progress. And this compression progress we now can plot in this kind of profile. It's now from now on called dx. Like x is this joint object, like this joint thing, the history of experiences and the new object. So we call that the complexity runtime profile. And there we basically plot the description length as a function of the runtime that the current compression takes to be computed. So you can also think of the time-bounded Kolmogorov complexity as a function of time. So there are certain aha moments that are only unlocked once we have a certain compute budget. Certain compressions are only possible if we have a lot of compute. And we can plot this function. And let's say we've done that. Our agent has already compressed it, while it had these insights about the data, compression progress, which are these drops in the profile. And now we stop. And now the question is, how will it continue? Do we expect there to be any more compression progress or not? I mean, we cannot know for sure because we have not spent the effort yet, but maybe there's something we can actually say. Okay, this is what we get about the expected future compression progress. Will there be any or not? And how much and how soon? So one thing to say is that the runtime of the last drop of an object, this is also called the logical depth. Okay, now the spoiler, we can actually say something about the expected compression progress. And what mostly determines it is what we would call stagnation length. So at a given observation cutoff, what determines by far the most the expected compression progress is how long we have not made any progress in the past, or how many steps have we been looking for a new progress but have made had no progress. And that actually, if we plot the expected future compression progress as a function of this stagnation length, then we see this exponential decay. We have not made any progress in a long time. It's very, very unlikely to make any progress. How can we actually show that? So this is exactly the profile that we have here. Again, like we have the runtime on the x-axis and the complexity of the description length on the y-axis, and we have these drops. Now there's another kind of profile, might call it the log size and complexity profile, which is related, but it's different. There we compute sets that contain an object X and plot the log cardinality of the log size of the set against the set's description length or complexity. And there we also have some kind of also have drops in the profile whenever like an additional complexity allows us to shrink the set size down. So if we find some criteria, like some pattern that holds for the object and that we can put into our description, and that actually reduces the number of objects in our set, that makes it more specific. And all these kind of profiles, there are some very nice results from algorithmic statistics. The slope always has at least, or it goes down by -1 or less, because we can always cut the set size in half by adding one more bit to the description length of the set. That's basically a trivial trade-off. And if we can do more than that, then we have a drop in the profile. But in principle, when we come up with a valid profile shape, there is at least one string that has a profile that looks like that, or very close to it. And another thing we can say is that number of strings that have a profile of a given shape depends almost exclusively on this distance. K is actually the Kolmogorov complexity of the string, and M, which is the position of the last drop, which is also sometimes called the sophistication string. And how many strings that exist with a given profile shape depends almost only on this distance between K and M. And then one third thing we need is that, also fascinating, is that these two profiles are extremely related. In fact, they are, for a given string, they are affine transforms of each other. If we rescale this profile here with the BC-Beaver function, the x-axis. So that means that, first of all, that means that logical depth and sophistication are basically two sides of the same coin. That also means that every drop in this profile corresponds to a drop in this profile. And whatever we can prove about this profile, we can also easily translate into a profile. Okay, and that's also, to actually now calculate the expected compression probability, we need one more ingredient, namely prior over computable objects. We already heard about this quite a bit, about the universal priors and monoprior and so on. So want to assign every object we might possibly encounter some probability. But since there are infinitely many computable objects, we cannot just put the uniform probability in something else. Maybe the easiest idea is what I call the length prior, which means like we heard about the monkey typing random bits already. So length prior would be how likely is a monkey to just type out the object directly. Then the shorter the object, the more likely, of course, it is that the monkey types exactly that. Then another type of prior is exactly the algorithmic or Solomonov or universal prior, where we give the monkey a universal computer or a universal prefix machine where it has to type in a program, and if it outputs, then we're measuring the probability of the monkey programming the computer so it outputs our given string. This prior has the disadvantage that it's uncomputable. We cannot really sample from it. Just the simple reason that if the monkey types in a program, we don't know if it will ever hold. So what do we do if it goes on running forever? And yeah, that's a halting problem essentially. We can fix that, and that's what Schmidhuber has done with the speed prior, basically by forcing the monkey not to only type in the program, but also a maximum runtime limit. So it just puts in some random runtime, and when the model, the program has not halted by then we just output the empty string. That essentially means that we put a logarithmic runtime penalty on the program or on the probability of the string. Okay, this as a prerequisite, and with these ingredients now we can calculate the expected feature compression progress if we observe some kind of partial profile. So this is again now some kind of profile shape, and let's say we observe it, we only observe the dark gray portion here. So we have a drop, and then we stop observing. And we're asking what is the expected continuation of this profile. And now we basically just count. We know that we can do with these results from algorithmic information, from algorithmic statistics. If you have no further drop, you have this blue curve here. We see here this diagonal element is very, very long. And this is what determines how many strings with this kind of profile exist. If we have a further drop, we have all these green cases, well, green continuations. There are many of them, but all of them have shorter diagonal lines. Means there are few of them. And now we basically just freeweight, like we weight the number of profiles with their prior probability, and we can calculate all these expectations and the probability that there will be a further drop and where it will be, and so on. And yeah, here are the results if you're interested in that, but maybe I will put some visualization maybe. 5 minutes? Yes, okay. Then I'll be very quick. I mean, here we can see basically those are the two profiles, and you can see how it changes if I move around like the shape of the profile, how it changes this here is the probability of a future drop. So as a function of the stagnation length, so the difference between T and M, like this distance here, and this is what overwhelmingly determines, you see, if it gets smaller, our probability of a future drop or future compression progress goes up. This is the important thing, and here down there we see the expected future compression progress, which is also what we care about. And we can also change, I mean, this is now for the length prior, for the algorithmic prior. It looks a bit different. Actually, we have higher probability of a future compression progress, and we have of a future drop, and we have higher expected compression progress. Okay, this is for the algorithmic prior, and finally the speed prior. Now something interesting happens, namely everything goes to zero, which has a simple reason, namely that I only mentioned it briefly, but when we here have this kind of complexity runtime profile, we had to rescale it with a PC-Beaver function, which is this function that grows faster than any computable function. It grows extremely fast. And that means if we have some kind of, even if it's only a logarithmic runtime penalty, which we have in the speed prior, then it's basically impossible of any longer runtime, any program with a longer runtime to even have any probability, because it's penalized. Like the runtimes are so huge that they're penalized so much, essentially probability zero. This also highlights one of the problems with this whole construction, namely that it involves essentially physically unrealizable runtimes. So the question is how relevant is that to practice? You don't really know it, but I did some small experiments to see if we can actually also do some empirical results that show the same thing. And essentially what we do is some exhaustive program search in these kind of Turing-complete computation domains. We have 3 of them, namely 2-tag system or post-tag systems. We have cellular automata, also already seen, and we also have the brainfuck programming language. Those are like, the nice thing about these languages is that they're it's very nice. Like almost any string is a valid program that actually runs, so we can do just enumerate the shortest programs and we'll get some results. Also very quickly show the demo for that. And so we just say for 2-tag systems, we just run all programs up to a certain length. So the programs look kind of like this, for example. It's random letters, does not matter right now. But we just implement all, we ran, I think, 120 million of different programs. And whenever 2 programs compute the same string, we let's say the same output, remember that. And then we can also basically draw the exact empirical equivalent to these complexity runtime profiles. And this is what we see here. So we have, for example, this program that computes a certain output in 7 steps. We have another program that computes the same output in 14 steps, and yet another program, which is shorter, that computes it in 33 steps. And basically here we have this Pareto boundary of length of the program and runtime of the program. And we just do that for many different output strings. And then we do some statistics and count how many there are, and we see basically exactly the same phenomenon, namely that the stagnation length, so the number of steps where we don't have a shorter program that computes the string, determines how likely it is that there will be another even shorter program if we have more runtime budget. And this is exactly the same kind of exponential decay that we proved in theory. So we see it also empirically. And do that also with the other languages, but that's time to show that now. Yes, but this is basically what the experiments show. We have this exponential decay. I mean, for the 2-tag system, it's most clear. For Rule 110 and Brainfuck, slightly less pronounced because there are just fewer programs that share strings that share the same programs. Even though we ran like 2 billion Brainfuck programs. So we have that, and we have the theoretical results. One thing I want to say now is, we have the experiment results for tiny programs with relatively short runtimes. We have the theory for absolutely gigantic, unrealizable runtimes. Actually, machine learning, what we do with neural networks and untrained models and so on, that all lives in the middle. So inductive interestingness is what I call that, because basically we can say that whatever we've seen observed in the past, that past compression progress predicts future compression progress. That's what I mean by that with interestingness. And the question is if that is true also for current machine learning methods like reasoning and chain of thought, just neural networks in general that we train with gradient descent, also scaling models like all the scaling law theory and so on. I feel like there are some connections, which I probably don't have time to go into the details now. But there are ways of mapping all these concepts that I've talked about, complexity, runtime profiles, all these log size and set complexity profiles to these different domains. For example, chain of thought reasoning. Whenever more reasoning tokens with a better answer, we can imagine that as a drop in this kind of profile. And maybe our results tell us if we tried to give the reasoning model more and more budget and the answer doesn't improve, it's just unlikely that it will improve with even more reasoning tokens. There are no guarantees, it's just probabilistic, but what we can kind of prove, in at least some sense, is that that is unlikely. And also deal with interpret the networks in gradient descent that way, compute final steps of gradient descent. Here on the x-axis, on the y-axis, we have to plot not just the trading loss, but also the model complexity, which is hard to quantify, I admit. And model scaling maybe also tells us something like that. Make the model a bit bigger and the loss doesn't go down. Maybe there's some reason to believe that we start going to need some new solution. Okay, how to finish things. What we've shown is that stagnation length, so the amount of time that we have made no progress, when some content agnostic heuristic of how much further progress we can expect. Content agnostic was we don't even look at the data. The content in this setting doesn't matter, which is maybe nice, but it's also, of course, a disadvantage. In real world scenarios, we know what the data is. We can maybe take that also into account. The kind of data is also, we have the very basic priors, like universal prior, speed prior, and so on. Maybe that's not realistic. Maybe our training data, for example, text on the internet or maybe biological systems and so on, maybe they're special. Maybe they have this property that I think they have this property that there's always more to discover. Like in nature, that's clearly the case. That's why we do science. We expect there to be more progress. There are new levels of emergence that we can describe. There are new secrets to unlock, and we just assume that that's the case. And because I'm not sure how to account for that and how to model that, I think that's very interesting from the work on complex system science. And yeah, just as a general message, I think it's important in machine learning and so on to think, and especially if you care about open-ended systems, because the self-improvement and so on, think about interestingness and about how models can develop a taste and a criterion of what to do next.